Hello, this presentation is about the chemistry that occurs within the plume of a volcano within the troposphere. I'll be presenting some observational data that gives some insight, and then the bulk of the talk will be about a modelling system we've developed to look deeper into. A quick note on the scope here. These observations and model output pertain to a degassing case. We're also doing some work on an explosive case, and we expect the chemistry in that plume to be not only quantitatively different, but also qualitatively distinct. Therefore, these results shouldn't be simply scaled up for substantially stronger emission cases. I'll mostly be talking about bromine, as this has the most exciting chemistry. Volcanoes emit halogens mostly as halogen halides. In the troposphere, HBr is the most interesting due to a chemical cycle known as the bromine explosion, which converts it to other forms of bromine. This is that cycle in diagram form. This cycle requires sunlight, so it only occurs during the day. It also requires an acidic aerosol phase. So in a volcanic plume, this is probably going to be sulfate aerosol. This cycle consumes a couple of ingredients, ozone and HO2 or CH3O2. I'll show how the bromine explosion can extract bromine from the HBr form. Imagine that we have almost all the bromine present as HBr, mostly dissolved in the aerosol phase, but 3 atoms as Br radicals. A full cycle going through the gas phase, and phospholysis reaction results in a doubling of this, the cost of 1 ozone and HO2. This autocatalytic nature is why this is called an explosion. The phospholysis of bromine monoxide would recreate ozone, making a null cycle between BRO and Br. However, if there is any other reduction pathway, either the full cycle going through the heterogeneous reactions or a shorter pathway, including the reaction of BRO of itself, you'd effectively destroy 1 ozone molecule for the cycle. If the bromine explosion occurred in a closed environment, eventually you'll run out of one or both of these ingredients. However, an actual plume will expand and mix in background air, resulting in more ozone or HO2 to be consumed. Another notable point here is that if all of the HBr is used up, then HCl can take its place. HCl, although less favoured than HBr as a reactant, is abundant in the plume and will never run out in any conceivable volcanic scenario. So if chloride is a reaction here, then BrCl is produced instead of Br2, and the photolysis of this releases a chlorine radical, which can have its own interesting chemistry. The balance between the different reduction pathways is interesting, and I'll return to that later in the talk. I've been generously granted permission to use some SO2 and ozone data that was collected as part of the GMOS flight campaign in summer 2012 around Etna. This animation shows the flight path, and the dot color is the plume intensity as measured by sulfur dioxide. And you can see it made lots of loops around, and we got various data. So I wrote an algorithm to identify major plume encounters. Because ozone can vary for non-volcanic reasons over space and time, this algorithm identified separate plume encounters, finding 19 of them, and then I looked at the ozone and SO2 variation within each. With 19 encounters, in almost all there is a clear trend. More SO2 equals less ozone. We see ozone varying by up to about 15 parts per billion, with plume intensity, as measured by SO2, going up to about 700 parts per billion. Although halogens weren't measured directly, this is all consistent with the theory discussed before. Given the distance from the volcano and measurements these were taken at, and assuming a wind speed, we can use the fairly constant gradient here to make a crude estimate of the ozone loss rate. This turns out similar to that estimated from a ground-based campaign I actually did at the same time, where I took ozone measurements within a few hundred meters of the vents. Now I'll turn to the modeling study. I've modified WRF-Chem, a 3D regional chemistry and transport model, to address this, adding in halogen and mercury chemistry, as well as an improved and more easily adjustable volcanic emission scheme. I used nested domains to model the area immediately around the volcano at 1 kilometer spatial resolution. All the results I show today are from this high-resolution nest. Shown here are the emissions from the volcano. It is modelled as a constant source of these species. The sulfur dioxide amount is calibrated using the aircraft campaigns, and the ratios to sulfur dioxide of various species are based on various in situ measurements. The species in red are species that aren't expected to be directly emitted from the volcano, but instead generated in a high temperature volatile air mix the first few seconds after emission. Notably, we have some bromine radicals to kickstart the bromine explosion. I also did some perturbations on this for investigative purpose, and these will come up in the next few slides. So here's our main case. Overall, where there is SO2 and during the daytime, there is reduced ozone. Here I show delta ozone, which is the difference between the main model run and one performed without any volcanic emissions. If we find model data that is effectively equivalent to the observational data, we get the same sort of ozone SO2 gradient. There's a bit of an offset that suggests we need to look at our initial and boundary conditions, but this gradient suggests that the chemistry here relating to ozone loss is mostly right. The most common measurements of halogen chemistry in plumes are actually BRO to SO2 column ratios. None were taken as part of the flight campaign, but our daytime modelled values here of order 10 to the minus 5 to 1 or 2 10 to the minus 4, and this pattern of a quick rise after emission followed by a levelling off matches general trends seen at Etna and other volcanoes. However, our model is not restricted to just bromine monoxide. This diagram shows the partitioning of bromine between various forms versus plume age, the animation cycling between midnight on the 30th and the end of the model 72 hours later. During the daytime, HBr is quickly consumed within minutes, and bromine monoxide and HOBr are the dominant species. For the first day, the 30th, this evolution is slower. This occurs because the wind speed is greater, which means a sparser plume and a generally slower chemistry. This is one of these perturbation outputs from a run where I assumed no high temperature products. Most importantly, no initial bromine radicals to kickstart the bromine explosion. Active bromine chemistry eventually occurs, but things are much, much slower in this case. I highlight a couple of things here that may be of interest to observation persons. One, because our volcano is a constant source, the wind speed directly controls the density of the plume. We find that with a lower plume density, the plume evolves slower. This is mostly due to slower uptake of HOBr on aerosol. This means that in a given time, the plume travels further but evolves slower. Because most observational studies use distance as their controlled variable, there's a potential for a double effect here. Two, the bromine monoxide HOBr balance, and hence bromine monoxide to SO2 ratios, depend on HO2, and this varies with time of day, with more bromine monoxide in the early morning and late evening compared to the middle of the day. Looking back onto ozone, this is a continual process. We can isolate the chemical effect from the physical mixing by ratioing the ozone loss to the plume tracer, SO2, and see that this is continual loss over time. One thing the model lets us do is actually determine rates of reaction cell by cell, reaction by reaction. The bromine cycle ends up looking like this. Stability of the different forms doesn't mean that no reactions are occurring, it's just that each species is being created as fast as it's being destroyed. Back in the introduction, I talked about how, although there is only one ozone loss reaction, there are multiple ways to reduce bromine monoxide HOBr. It turns out that for the evolved stable plume, the heterogeneous reactions are responsible for only a small fraction of the bromine reduction in the plume. That's not to say they're not important, especially the chloride reaction, which is the reason we have reactive chlorine present. However, for every big bromine cycle going through the liquid phase, we have multiple smaller bonus loops, which increase the ozone loss. So here we investigate what happens if we adjust the halogen emission flux while keeping all other emissions the same. We plot ozone loss in the same part of the plume as a function of the bromine emission flux, so we're varying across different perturbation runs. And we get a trend line here that has both linear and quadratic terms. This is because of the different ozone reduction pathways. Halogen oxide reactions, we would expect to scale with the square of the amount of halogens, or HOBR photolysis and uptake to aerosol would be linear with the amount of halogens. I'll quickly run through some of the other findings. We find that OH is depleted in the plume due to its reaction with SO2. This in turn increases the chemical lifetime of SO2 within the plume. Halogen chemistry reduces HO2 concentrations moderately in this degassing case. The model also reproduces two phenomena related to reacting nitrogen. With BrNO3 as an intermediary form, NOx in the plume, whether volcanogenic or from the background, is converted to nitric acid. We also find that any aerosol phase nitric acid within the background air that mixes into the plume is displaced by hydrochloric or sulfuric acid. These two effects result in a plume that is enriched in gas phase nitric acid. The photolysis of BrCl produces chlorine radicals. These reduce the methane lifetime within the plume, although it's still long. These chlorine radicals also react with ozone and produce chlorine oxides, OClO and ClO. And these are species which have been observed in the plumes of some volcanoes in approximately the amounts seen in this modelling study. So to conclude, ozone depleting chemistry occurs within the plume of a degassing volcano, and Wolfchem volcano is able to reproduce this. We can then look deeper into the chemistry and figure out what's going on. We'll be releasing the code of this modelling system with publication, and I'd be happy to discuss with anybody listening to this what we could be doing with this. Thank you very much for listening.